So, hello everyone, and welcome to this Research Days event. My name is Ilya, and I will be your conversation leader for today. With me here are our wonderful speakers, who I'm delighted to introduce, Dr. Gabriel Skalusub and Dr. Gil Einziger from Ben Gurion University of the Negev, Israel. And today they are going to share with us a bit of their immense knowledge about caching in general. And they will also tell us a bit about their research on advanced caching in particular. As staff told, please feel free to leave whatever questions you might have in the session chat, and I will make sure they reach the speakers as soon as possible. So, Gabi and Gil, would you like to add anything about yourselves before we start?
So I will add just one more comment, sorry. You're also welcome to jump in like I did now and ask a question. So of course we will address it according to the presentation, but a free discussion is always welcome. So if you're one of those, please join. And
Thank you, Stav.
Gabi and Gil, please go ahead.
Okay, so my name is Gil. I've been working in caching for almost 10 years now since I started my PhD. And over the years, this stuff evolves and becomes more elaborate and closer to real problems. And this is what the talk today is about. We are going to talk about caching heterogeneous stuff in heterogeneous places. So we are going to start from the very, very basic, like the research I did when I was a PhD, and we're going to finish 10 years later in the research I do right now with Gabi and many students and so forth. Gabi, you want to say a few words?
No, well, my background is networking algorithms in general, optimization, and well, the only thing I'd mention maybe is that if you want to get a position in VGU, you have to have either a B, a G, or a U in your name. That's why Gil and I both share the G's, and that's it.
All right, so what exactly are we going to talk about today?
Okay, so what are we going to talk about? We'll have 4 chapters in today's chat. The first one will talk about caching policies and why there is more to caching than LRU. The next one, we're going to show you that, well, caching policies is nice and dandy, but what we really want is adaptive caching policies that adapt to the current situation. And I'll try to explain why we need these policies, even if we're all very smart and we know all the policies and can implement all of them. And then Gabi will, Gabi will take over, and he will show you some other problems on caching, namely access strategies. We'll start talking about the user perspective rather than the cache perspective, and show that when you have multiple caches in different places, then simply selecting which ones to access is sort of a risk management game. And the last one will be our current research, like happening right now in collaboration with Red Hat, is where we want to reach something we call predictive caching, which is caching that is not restricted to looking at the past and try to see what will happen. It also detect patterns using perhaps machine learning techniques, and it treats items as streams of excesses that change in time, which is something that doesn't exist. That we hope that it's not science fiction. We want to convince you that it's not science fiction. Okay, so let's start. And the beginning, we're talking about cache policies. So I already mentioned cache a few times, so just for the record, or let's say what it is. So a cache is a fast but small memory, and we assume that this memory is somehow faster than what we call the main storage or the real storage. Caches are not always between memory hierarchies. Some caches are, for example, computational caches, where if I have a very complicated query that takes a long time to execute, I can avoid executing it twice and keep the results. But essentially, the cache needs to save us some resource. What we want to do, we want to serve most of the requests from the cache. And the more requests we serve from the cache, the more benefit we give. We reduce the average cost of a request. Okay, so the first thing about caches is a cache management policy, and I think that most people, at least until a decade ago, will tell you that cache is LRU, and they would be surprised that there are more algorithms except LRU. So let's see what LRU is. It's short for least recently used, the first policy implemented by Intel on their first computers. And everybody flowed with it ever since. So let's assume that I have this cache and I have 4 items in the cache. And for simplicity, I just abstract them as colors. And now one of these items, the red one, is accessed. So my caches are, my LRU cache is ordered by access frequency. So once the red one is accessed, I move the red one to the end, and I'm done. The interesting part happens in a cache piece. So now there is access to something which is not in the cache. In that case, I admit the new item to the cache, and evict, there was a yellow item there, and it's not there anymore because it was the least recently used items. So LRU are very simple, and they work very well for some workloads, and people use them all the time. But let's say they are not always a good idea, and in many workloads, for example, networking or storage, or when you have many users, what you really want is something which is called LFU. So what is LFU? It's my cache doesn't see all the little details of one user, and if we access the single piece of memory, then it's going to maybe use that memory again and access it again, like LRU does, which was designed originally for processors running a single process at a time, which made sense in that perspective. But now we have a cache, let's say, sitting on a router or network equipment or some server, and there are many, many clients. And from that perspective, what we see is a distribution. Some items are accessed more than others, some less. And the best thing the cache can hope to accomplish is to find the top items in this distribution and put them in the cache. And LFU for a long time, until perhaps my PhD, didn't have a very natural algorithm to it. because essentially what we need from LFU is we need to count like how many times we've seen each item, and then we need to count on some to age discount some time, otherwise it wouldn't work very well, because if I count how much I've seen stuff since the beginning of time, then I'm very slow to detect new stuff, and things change in caching, even in LFU. So the first thing I'm going to do is I'm going to talk a little bit about this LFU and how I model it. So basically, cache policy is composed of two decisions. One of the decisions is which item to evict if I want to add an item to a full cache. So the cache size is limited, and if I want to add an item, I probably need to drop an item in a return. So an eviction policy basically says one of you guys should leave because we want to insert the new guy. And then we select the cache victim. Here comes the admission policy, and this is why I said in LFU, in LRU, we admit the new item and evict the LRU victim, because part of the thing I think that was new in my PhD is to explain to people that admission is a decision, and a little start to people that are not doing flash caching. These guys knew it because they wanted to preserve the lifetime of flash, and they understood that every time they write to the flash, they pay something. But aside from these guys, most people didn't even say what their admission policy was. They didn't explicitly use the term. So what I say, the admission policy received the cache victim and the new items, and essentially it needs to make a decision. Either it wants to add the new item to the cache at the expense of the cache victim, or it wants to keep the cache victim and add the new item, and drop the new item. And it essentially asks, according to some heuristic, which of these items would be more beneficial to the cache. And now, if you look, I'm going to take you one slide back. If you look at this distribution and say that the workload is very LFU, then the common answer would be, I don't want to admit anything. And why do I say no in the admission policy? Because if I'm so smart and my cache is so good and I manage to find all the red items, then I already have all the good things in my cache, and I don't need any new things coming and polluting, in a sense, my cache. Like, I'm not going to give up a very good item for a very poor item, and all the good items are already members of my cache. So most of the time when I use the admission policy actually says, no, I don't want this item in the cache. Okay? Now I'm confused.
Ilan, we have a small remark on the LFU slide, which says that basically this graph would not accurately describe all use cases, but in case of a second level cache, the red part would be absorbed by the level 1.
So as we say in this lecture, and I say from the beginning, LRU and LFU and anything in between are heuristics. Sometimes they work very well, sometimes they don't work. In many cases, like hierarchical caches or distributed caches, we want to do something extra, and we'll even talk about these cases in these lectures. So right now we're like at the very, very low level of a single cache, no hierarchies, and just some of the philosophies or the main heuristics of how to manage it. Okay, so now comes the question of how can we tell which item is better? And here's come the maybe ugly part, or the part that takes some effort. I actually need to count. how many times I see each item. So I'm not actually counting. I use all sorts of techniques like bloom filters and counting sketches to approximately count. And it's okay to approximately count because counting how many times I've seen stuff in the past to guess how many times I'm going to see them in the future is already an approximation. So no point in being precise if you're already doing an approximation by design, because we really don't know the future. And no reason not to be precise if you have the resources, but it is many resources. There is some blog that say that they were precise, and then they tried our library and they saved a few gigabytes of memory per server, and they were very happy about the experience. The less demands, but of course you can always be precise. So what we do every time something arrives, we count it, and we count and we count until we say we have enough. So in this example, 10 items is enough. And then I don't know what to do, so I just divide everything by 2. And what happens now? The relative order of things remains the same, but this is integer division. This means that 1s go to 0, and 3s goes to 1. So I lose information, but now all stuff is forgotten, and I have and can use the space I use to count again. And we want this window to be perhaps, let's say, 10 times the size of the cache to give us the perspective on the one end of the distribution, but we don't want it to be too large because workloads, even real workloads, even LFU workloads where LFU works very good, they also change over time. So the more we keep statistics, the more accurately we know the order between the items and which are the top items and which are not. But the slower we are to discover changes. Let's say if something was very, very popular, let's say it has a frequency of 20, and now it stops coming. That's it, finito. I'm not going to see this item anymore. So first time I divide everything by 2, 20 becomes 10. Okay, 10 is still very popular, it's still in the cache. Second time it arrives, nothing happens, 10 remains 10, 5, and then 5 becomes 3, and 3 becomes 1, and 1 becomes 0 after log of 10. What I call reset operations. I forgot everything about this heavy hitter that have been very attractive in the past, but is no longer attractive anymore. So this is what we call aging, and there are many ways to do it, and I'm not saying that this particular way is the best one. I'm just saying that this one works, and every other reasonable way where you eventually forget old stuff would work as well. This one we can implement with very little space. Okay. And basically here I'm going to end my chapter about cache policies, because essentially what happened with the LFU is that I got an initial success, and it was adapted to Caffeine Java caching library, and many people used it. But many people use the competing library. And then we say, why can't we be better than the competing library? And the reason is because we picked a cache policy, and they picked a cache policy. They picked LRU, and we picked LFU, my version, tiny LFU, never mind. And on some workload, you see the orange line is better than the blue line, and LFU works better. The search engine is a classic example because the search engine sees many clients, and distribution is the right way to look at its work. or is a better way than the recency. Other things like build cache, where people constantly update their softwares and they want to take precompiled files. Basically, if you created a new version of a library, then the old version will not be accessed anymore. So everyone wants the most recently accessed version of each library they use to quickly compile their projects. So in build caches, what works is recency and not frequency. And there are many other workloads where you either want recency or frequency or something in between. And now the problem is every algorithm that I'm going to teach you will work better on one workload and worse on the other. So when we talked about how to grow our library, how to grow Caffeine, we understood that we somehow need to behave like LRU when LRU is the best, and like LFU when LFU is the best, and somewhere in between for all the cases in between, because otherwise we can't really become, we can't really take the market, because some people just say the other library is better for our workload and your library is not good for our workload. So we want to be good on every workload, because this will give us a library that you can always use and get something competitive. Okay, so what we want is something that always works, a silver bullet that removes the need for the users to actually understand what caching is, how does it work, what workloads they have, what heuristics works and do not work on their workloads, implement a few cache algorithms, collect data, run all these experiments. And this stuff I did with a few open source projects, and it took us about 2 years every time. So if we solve this problem, adaptation becomes a lot easier by users because they don't need to do this. We do the adaptation for them.
Gil, we have a question in the chat. So if clients could be trusted and cooperative, it would have been nice of them to provide a keep in cache / do not bother hints to the server. So yeah, so that's one way of addressing that.
Yeah, I agree. I totally agree. What can I say?
And I had a question about the previous slide.
It's been used, people use it, it works in some domain. I don't mention it in this talk because right now I'm talking about algorithms that work for any domain. So I'm not assuming that my clients are kind and give me additional information, but of course, any additional information helps.
All right, so as we are in the beginning of Act 2, this is a great time to ask questions about Act 1, either live or in the chat, as you prefer. And now, when you're talking about this silver bullet, so are you referring to finding a sweet spot between LRU and LFU? So kind of a combination of the two, or maybe it is more to it. So you could use kind of a third heuristic, fourth heuristic, and so on, or maybe completely different approach.
So actually what I want in a silver bullet is I want not to lose. If I go back one slide, you see that my winner on one trace is a very bad loser on the other. Like I have something that works for me great on one trace, but on the other trace is a catastrophe. We can get, 80% hit ratio and we're getting 10. So I don't mind getting, 70% instead of 20%, 75%. I don't need to be the best in the world from all the algorithms that exist on this particular workload. What I really need to do is never lose by a big margin, because once you chose the orange algorithm in the left workload, and now your boss is angry that nothing works and everything works poorly. And why did you choose such an idiotic algorithm for your workload? And then you're very offended because it's your PhD. What can you do? So actually, the important thing, at least from my perspective, is not to lose. You don't have to win. You just don't have to lose badly.
Right, and
So what Peter suggests of using both algorithms and using the one performed better at the moment, it's actually an approach which is feasible, and some of my colleagues even suggested it. They did what called miniature simulations, and it's valid and possible and a little bit expensive. But usually, if it does the work, it's worth the effort, and it's one way to do adaptivity, and it works. So it's a good way, and they have a very nice work about it.
All right, so I believe we can proceed further. We have one further remark from Yaniv about the problem of cache and whether we can do some profile guided optimization. I assume we are going to cover it next.
So what Yaniv is talking is very similar to the stuff that Gabi will be talking about at the end of this lecture, when we're moving from basic patterns like LRU and LFU to seeing things, seeing patterns that happen once and maybe repeat twice. Your program, usually if you don't write it just to confuse the cache, it's basically, it has some flow to it, some patterns that it creates when it accesses memory. First you access one file, and then you access another, and then you access the third file, and maybe then you have a branch. Either you access a fourth file or you access a fifth file. But these things are not that complicated that we couldn't possibly understand them if we see them over and over again. Or at least we really hope so that we can understand them by seeing them over and over again. But this is exactly the direction that our research is going. We're putting a lot of our effort on these capabilities.
All right, great. So let's proceed to Act 2.
So our next work, when we started understanding that we want something that can be recency biased or like LRU or like LFU or anything in between, what we say is we want two caches. The first cache works on one heuristic, and the second cache works on the other heuristic, and now we are free to size these caches for each workload. So some workload would want me to take the window cache which has LRU and just enlarge it and use 99% window cache and just 1% for LFU. While other workload will say, let's do 99% LFU and 1% LRU just for the flavor in case something LRU comes along. Another will say, I want 20/80 or any other balance. And each partition of these caches would give us a different cache policy with other trade-offs. So let's go over the schema a little bit, just to understand it. So new items are always added to the window cache. And when the window cache is full, it selects a cache victim. So we have a window cache victim. And now the window cache victim has a chance to be admitted to the frequency-based cache. So the frequency-based cache selected its we call it main cache, because initially the main cache was 99% and the window cache was 1%. The admission policy has to select which one is more attractive to the LFU cache, the window cache or the main cache. What it does, it looks in its data structures and decides which one of them it has seen more times in the past, and the one which is more frequent will be the winner and will be entered to the main cache. So the cache victim of this policy is either the one from the window cache or the one from the main cache, depending on admission or no admission to the main cache. So this is our policy. And basically what we see for all kinds of traces, we see that when we change the window cache or the LRU cache size, we get something that works better in places where large window caches are preferred. So if you look at the build cache in Gradle, you see the hit ratio on the y-axis and the window cache percentage on the left axis, and there are two algorithms here. One of my design, what I showed you, and the other one, algorithm of my colleagues. And both of them has these two caches structure, which is why I put them in the same graph. And what you see is the more I increase the window cache, the better hit ratio I get for the same cache size. And now the search engine where LFU works best, you see that a small window cache of 0 is the best, and the more I increase the window cache, the less things work. So everything goes down. But perhaps the more interested are other traces like financial transactions, where we actually see that no window cache of 0 is not good. Then I increase the window cache, performance improves. But depending on the cache size, the different lines are different cache size. Eventually, I get to a point where increasing the window cache more will decrease my performance. So there is a sweet spot somewhere, and this sweet spot is different between one algorithm to the next and between one cache size to the next. So I can't just say this workload requires 20% window cache, because then I increase the cache size and it wants 25% or 15%. So I keep information on many items. I showed you a few slides ago that I have this data structure, and once in a while I divide by 2 and forget all the things that get 0. And basically I don't remember just stuff from the cache, I remember also a lot of stuff that is not from the cache, and the reason I can get away with it, or my colleagues let me get away with it, is because I don't do it in an expensive, memory intense manner, and the entire cost of TinyLFU for remembering about 10 times the number of accesses, the 10 times the cache size in accesses is about 1 pointer per cache item. It's like 8 bytes per cache item. So we use a conceptually large metadata about many accesses that are not only for items in the cache, but I abstracted all the technical details, but we do it in a way that it costs very little computation and space. We use approximation algorithms for it, which is another field which I can go for 2 hours and talk to you about approximation algorithms. And this is why we get away with using such a large histories. And in a more philosophical way, there is the places where LFU improves, and the reason that people didn't use LFU before my PhD is because these large histories always were seen as a problem in the literature. Okay, so this was question answering. Any more questions, or should I go on?
I think you can go.
Okay. So what we're going to talk now is about our adaptive cache policy, which is adaptive TinyLFU, which in a gist, it plays with the balance between the LRU cache and the LFU cache, and it tries to find a reasonable balance. I wouldn't say the best balance, because by design I created an algorithm that does not converge on purpose, and I will explain you why I'm such stubborn about it. And this one actually was very successful. Once we came up with the adaptive algorithm, the user base of caffeine almost tripled, and with de facto became like the monopoly on Java. If before us everyone used LRU and they used the library by Google, after us like 80% or something like this use caffeine, and they all use like state-of-the-art adaptive policy, which is sometimes LRU, sometimes LFU, and a lot of stuff in between. And the next thing I'm going to talk about is delay-aware adaptive window tiny LFU. And this one actually starts being the heterogeneous stuff. Basically, in some workloads, the items are not all the same. Some items, for example, consider DNS or search engine. Some search queries take longer to compute than others. Some DNS entries comes from further apart in the internet than others. If you access web objects in your browsers and you cache them, some items are also cached in your ISP caches or in CDNs along the way, and others are not. So the benefit you see from caching one item is not always the same as the benefit of caching another item. Some items have larger miss penalties than others. So the next one will try to expand our horizon a little bit and see how we can handle with things which are not all equal and differ only in their access, in their frequency or in their access pattern, but also in the hit and miss time of things. So let's get going. So those of you that know adaptive cache algorithms probably know that most algorithms in the literature, they are very fast algorithms. They work very quickly. For example, IBM's ARC, it makes a very small step for every request that arrives. Either it makes the LRU cache larger or it makes the LFU cache larger, and it decides so for every point, for every query that arrives, every request, it makes a small decision. And this one was so, like all the examples we've seen when we came to design an adaptive algorithm, all the examples we've seen behaved in that particular manner. And it took us about half a year to understand that this would not work for us. And why wouldn't it work for us? Well, it worked for our competitors because they have ghost entries and they can say upon a cache miss, if increase in the LRU cache or increase in the LFU cache would have caught. They ask for a miss, they ask which cache should I increase to make it a hit. So they build this data structure especially for adaptivity. So it allows them to make small changes very fast. But our goal when designing Widow Tiny LFU was for scalability and especially compactness. We wanted everything to be small. I just had my children and everything looked tiny to me at the moment, and this was my focus in life at the time. And basically when you compact everything, we don't even remember the order of accesses. So we don't have enough information to make fast decisions. So our approach was statistical one. I'm going to make very large, very infrequent steps. Like I'm going to increase the LRU cache size by 5% of the total cache, which is big. It's not something that would converge. It's and then I'm going to wait millions of requests, maybe tens of thousands, sometimes millions. I'm going to wait perhaps 10 times the cache size, maybe 20 times the cache size. And after that, I would ask, did the hit ratio improve? Like I made a change, I didn't know if it would help or not. But after 2 million accesses, I can say, did it work or did it not work? If it works, well, let's do that again. Let's make the window cache 5% bigger. and repeat the measurement, and then we do, and we measure again, and we compare the hit ratio of the next epoch and say, did it improve the hit ratio, yes or no? And surprisingly, this is the algorithm that caffeine used today with the 5% and with the very large adaptation intervals. And if there are machine learning people in the literature, when we used all the very sophisticated climbers taken from machine learning, and Nestor momentum, and all, and we really made an effort to come up with an algorithm that converges. And some of them, I think, are slightly better than this one, but they are a lot more complex. And this complexity exposes corner cases, and we can't guarantee that the algorithm would not get stuck and stuff like this. So eventually what we like voted on the project, what people get when they download the caffeine library, is the very simple hill climber we started with the 5% changes, which are very big, and the very slow decision time. And the logic behind this is that we know a cache system, it works forever. If you're doing experiments as a student, maybe it doesn't work forever because you want to graduate. But once you have a product or a system or a data center, it goes for a day and 2 days and 3 days and so forth. So it doesn't really matter if it takes it an hour to initially when you start, it takes it an hour to start working very good. So what? It still have months to run. So let's see some graphs. So here I go back to a workload where LRU is like the best and my non-adaptive algorithms are the worst. So these two are two versions of my PhD algorithm. One of them is very simple, and the other one is the one I showed you with two caches for frequency and for recency, LRU and LFU. But the LFU is always 99% LFU and 1% LRU. There is a story, interesting story of why 1% LRU, but never mind that for now. What we've seen is that eventually my adaptive algorithms choose a configuration which is very similar to LRU because if you look, we have 3 lines close to the purple line of LRU, which means that they basically increase the window size very big. But, and there is a but, remember we only do percents of steps of 5%, and we do not converge. And this means that once I get to 100% LRU, sometimes the hit ratio is just a little bit smaller than the previous step, and I would go to 95% LRU. And then maybe I was unlucky again, and now I go to 90. So what I have is like a drunk hill climber algorithm that never converges, that keeps like a drunk walk across the optimal configuration, and this is why I get a little less than LRU, but it's not that drunk in the sense that I still do much better than being in the wrong configuration. So what we managed to do is a little bit more modest in finding the best configuration and sticking with it. It's not losing. Okay, we're always slightly worse than the best configuration. And here I show you the same thing, but the best static configuration is the green one, which is not LRU or LFU, it's somewhere in between. So here I didn't have some algorithm that attains the best result, one of mine, but how would you know that you need to select 20% to get the best result? And as you see, the blue line is almost as good as the green line. It's not as good because the hill timer is perhaps by design imperfect and unambitious, and it does not converge, and it makes very large steps, and it will never find the exact point. So if it needs to find 20, it will sometimes be 15 and sometimes 25, and maybe it will go to 30 and to 10 occasionally, but it won't be, but it will be around it will sort of hover around in the good area, never finding the exact best balance. And what I said in the research paper about adaptive caching, that this is enough, because the problem is not getting the best possible cache policy for a workload. The problem is that if you don't use an adaptive policy, you have to do research. You have to do a performance study. And to do a performance study, you need traces. And then you need to model a few cache policies. And then you need to compare them. And once you did all that and it took you 2 years, tomorrow comes a new client, and this client has a different workload. And what the configuration you selected is not good for that client. So essentially the adaptivity, in a sense, it lets every client get cache policy which is configured according to the workload that that client sees. The problem we solve is not of algorithms, it's a software engineering problem. I want to come to people and say, I have a solution for you, and you can just take this library, use it, and it will be all right. You'll get an optimized cache policy. You don't need to do anything else. Yes, the lack of convergence, like Peter states, give us more rapid adaptation when workload characteristics change. This is why we didn't manage to converge. We actually know how to converge very well. We start doing smaller steps, and then we doing them and then we need a lot more time to verify that the smaller step is correct. Because if I do 5% change in the caches, then I'm going to see maybe 1% in the iteration change. But if I do a 10th of a percent, I'm going to see a very, very tiny change in the hit ratio. So I will take a lot of time before I would be sure that I see an improvement and not just statistical noise. And then the problem is that the workload, by the time I'm converging, the workload changes. And basically, it's like it's a problem where I don't know. Life happens while you make decisions, and this is why eventually, after trying for a year, it was very frustrating because I spent a lot of time in it. But after trying all sorts of very smart momentum-based and other techniques where the step size we make is not constant and we can converge, we eventually didn't get enough confidence in this method that they would always work. So we actually never publicly suggested all the more sophisticated hill climber algorithms that we developed because of that. So they remain in the simulator, and maybe one day I'll have like a genius student that can figure it out. But essentially, right now we have this imperfect system, and it's, for software engineering perspective, it's good enough. Maybe my algorithm person is not happy, but my engineer is very happy. Okay. Any more questions, or should I go on?
Gil, I think we should proceed, given the time constraints,
So
to the next
right now
part.
I'm going to wrap up adaptive time LFU, which is basically competitive, and you get an optimized policy, and it's an open source project that you can get, and it's working for millions of people, and just use it. The last thing I'm going to do, and I'm going to be a little brief here because I want to leave Gabi also enough time to talk about his stuff. I'm going to talk about delay-aware admission policy about Omri's thesis, a student who just graduated. And basically what we say, like I already told you about it in a sense that some stuff takes longer to be, some misses are more painful than others. So what Omri say, let's measure everything. We measure how much time we wait on every cache miss, and we measure how much time it takes us to satisfy a cache hit. And if, for example, you need to do stuff like fetch the metadata or check that your entry is valid, all this stuff is part of what you do upon a cache hit. So we measure this, and then and the benefit we can get by caching an item is the miss time of that item minus the hit time of that item. The miss time should be larger, otherwise no point in caching these items, but we did find on real workloads that some items are actually faster to miss than to hit. This is very outliers, but it happens sometimes. And so some items should not be cached. And for frequency, for tiny LFU, if before we asked if the frequency of one item is bigger than the other, anything that changes now, we take this benefit, like how many milliseconds of access time is saved for every access, and we time it in the frequency, tiny LFU says, we multiply it, and basically it gives us how much time we would save by caching item X. And now I'm going to show you an algorithm which is completely different and exactly the same, which is why I love Omri's work. You have seen this drawing, and essentially the only thing that Omri changed is that the admission policy, instead of frequency, it asks about score, and this score already the access latency to the cache. So Omri instead actually did very little, but this little is competitive with state-of-the-art approaches that built elaborate algorithms, especially for heterogeneous caching, where each item has different costs associated with it. And I'll show you a graph or two. And
Gil, I think we will omit the
I'm
evaluation if you
finishing here. And to tell you that the red line, the best one here and here is Omri's lines, and all the others are algorithms especially designed for this heterogeneous problem. And what I like about Omri's algorithm is because it's general use. We use measurements. We don't know if you have a memory hierarchy, if there is computation cost. You don't tell us the cost. We see the costs ourselves. We adapt to changes. And perhaps the most important stuff, at least for practitioners, the academics people really hate that. For practitioners, for me, the most important part is that it's incremental. We build the cache policy by small increments, and every time we add another layer to the policy, eventually having a policy that nobody else would be able to compete, like Google or not. I like competition, and I don't make any money of it, so I don't mind if someone beats us. But it gets harder and harder each year because our algorithms become more sophisticated very gradually. And Omri's step is just another incremental step. So here I'll handle the torch to Gabi and let him tell you about access strategies and streaming and all sorts of interesting.
And thanks, Peter, for the reference. I'm sure Gil and Gabi will take a look at it.
Yeah, thanks to everyone contributing and being active in the chat. Gil, could you let me share?
Okay. Should I stop sharing for you to start?
Yeah.
Okay, so I start.
Okay, good. Hope everyone can see my screen. Yeah, should work. Good. Okay, so we're now in Act 3 of our talk, and I'll be sort of like using Gil's the place where Gil just stopped about the fact that if we cache things in heterogeneous places, we get like distinct delays and might make different decisions and we'll be talking about access strategies and streaming models. So assume that we have like a request for an item, and we're actually trying to retrieve that item or check that item if it exists in one of several data stores or caches that might be located somewhere in our system. And when we try to do those things and access an item there are two things we have to handle. One of them is uncertain content, especially for caches. Like if these places are caches and we want to retrieve things from them, at any point in time, we're not sure if our item is there or not. I mean, there is a true answer. Some data store, some cache could actually have that item, like in here, and some might not, like data store 1, which doesn't contain it. But we're not sure about that at any point in time. And the other element that we'd like to tackle or address is the fact that accessing these data stores might induce heterogeneous cost. I mean, accessing data store 1 might be more costly than accessing data store 2, and these costs could be related to simple latency or actually money or load balancing issues that affect and provide and give us distinct costs for accessing each of those. And what we'd like to propose or show or present is actually algorithms that address these two issues when we have to make a decision to which data store should we access. So the first problem we'd like to consider is that of reducing uncertainty. So what we'll be considering is actually having indicators of cache content. So these indicators are actually very small approximate digests of the content. So like if the data store would like to tell us its entire content at every given time, that of course would be great, but will not be scalable if we want to make a lot of requests and make a lot of accesses to each of these data stores. So what we could get is just like a small digest that actually could be sent periodically. We don't have to have like a fresh digest at any point in time. And these digests they give us like a hint of whether or not this item is actually available in each of these data stores. A very common example of such digests or such indicators are just Bloom filters, which are like very compact data structures that tell us, give us an indication of whether or not this item is actually in the data store or not. Specifically, Bloom filters usually induce only false positives. I mean, they might err. I mean, they might give us the wrong answer. Like, for example, in this case, for data store 1, the indicator says, yes, that item is available in the data store, although the real answer is no. And sometimes they give us the correct answer, but it's just a one-sided error type of thing. And the smaller the digest that we use, of course, the larger the error. Right? I mean, if we are able to use a digest that can actually give us a full description of the entire content, that would be great. We won't have any error, but that would be very, very large. So the smaller the digest, the larger the error. So we're going to use these indicators as a way to mitigate the effects of uncertainty on our decision making of which data store to access. And the second aspect is the fact that we have distinct costs for accessing each of those data stores or caches, remote caches. Basically, we can access several of them, but we would like to pick the right ones to access. We wouldn't want to access all of them all of the time. I mean, again, that depends on the cost, but we would like to be as efficient as possible in this respect. So we have these costs, and in case that we access some subset of the data source, some of the caches, but don't find the item in any of them, then this usually would bear a large penalty of going to like a remote repository and actually retrieve it from the original server that has it. So there's some missed penalty associated with not finding the item in any of the data stores that we try to access. So we've developed several algorithms for this problem and models, which I would not go into the math of it, but I would like to give you like a gist of how might this be useful in a real scenario? So here we've taken like the outline, the topology of the OVH data center distribution. OVH is a cloud provider or CDN provider that has several various points of presence in the world, and we've taken like a snapshot of that in 2018 and induced and like projected that onto our model, this network. So assume we have a client somewhere in this network that wants to access and find some item, and it gets a positive indication from some subset of the repositories, the caches available throughout that network. Some of these indications might be wrong. I mean, remember, there is some chance of false positive. Some of them are wrong. Some of them are true. I don't know which one is which, of course. Some of them might not give me any indication that it's there, so I'm going to leave those out because for example, for Bloom filters, we assume we don't have any false negatives. And now I have to make a decision. Which of these should I access? For that decision, we have to have like a cost model of how much would it cost us to reach each of those data stores, remote data stores, and we've built some access cost distribution for accessing the distinct data stores, which actually depend upon the available bandwidth and the induced latency that we would get for accessing those data stores, which is derived from the actual values and the bandwidths available in this network, like a shortest path kind of thing. And we get some distribution of costs for accessing the distinct data stores. We've developed several algorithms for this. They are all approximation algorithms. So they are heuristics for which we can provide guarantees as to their performance, the worst case performance compared to the optimum performance possible. And what I'd like to show is some results of how some of our algorithms, actually one of them, does compared to, well, like natural approaches that you might take when addressing this, when trying to solve this problem. So these are some of the results for our evaluation of these algorithms. So I'll just describe what you see here shortly. So first of all, the policies that we're considering. So DSNAP here, the third one in each block, is one of our proposed algorithms. Cheapest is actually the policy that just goes to the accesses the cheapest data store that provided a positive indication. All just says just access all of the data stores with a positive indication. And so this is for the policies. For the different columns, that they differ by the number of locations in which we store each item. You can think about this as like the redundancy or multiplicative. I mean, how many places do I store an item? So of course, the more places we store an item, the more likely we are to maybe find it in a data store that provides us a positive indication. And here on the left, we have the missed penalties of how costly would it be to actually not find the item in any of the data stores that we've accessed. And as you can see, without knowing the distribution of, I mean, I don't know where the actual location of each item is. Our algorithm performs pretty well, or in a sense better than all others, regardless of the number of locations this item might be found in. These results, these numbers are actually the normalized costs compared to the clairvoyant algorithm that actually knows where each item is and has no false positives, and like it really knows the content of each of the caches. So we're paying like roughly 10%, no more than 10% more than that clairvoyant, where the alternatives, depending on the miss penalty, might be as large as 20% in one location, or more than 56% more than the clairvoyant in 5 locations. Any questions on this part? I mean, I didn't follow the chat, so if there are any questions.
That's fine. I think we can go.
Okay, great. So what we've just seen is a model for deciding which data store or cache to access with heterogeneous costs. And I remind you that we also consider the heterogeneity in terms of sizes, especially large objects, where caching large objects locally might be challenging because that might just like use up the entire cache that we have. So what we propose here is to actually cache locally only parts of objects, and specifically prefixes of objects, in order to mask the delays that we get from accessing items in remote locations. So how would this look like? So here you'd have like some idle time, some wait time you have to wait to get an item stored in the cache. And this would be the time you'd have to wait until you get the item if you try to retrieve it from the remote storage. And the idea here is to actually not store the entire item in the cache, but just a relatively short prefix of it, such that by the time we retrieve the short prefix from the cache, we can now move on to retrieving the remainder of that item from the remote storage. So we initially issue the request both to the cache and the remote storage. We get the prefix quickly from the cache, if it's a cache hit, of course, and the remainder we get from the remote storage. For the client, the perceived service of getting this item looks like something like this. So this is like as if we were getting this item that was completely stored in the cache. So this is what we propose to do in this context. Store only parts of the items, specifically the prefixes, in order to mask or camouflage the fact that we have large latencies to the remote storage. Okay. So this essentially means that we expect the best, right? We want to, if we expect a request for a large object, we will cache the prefix, serve the remainder from the remote storage. And this is essentially a streaming model where we get distinct chunks in a streaming manner from of this object that we're trying to retrieve. Another view of this would be that actually, if we get a request for the prefix, this implies that the remainder of the item will also be requested very, very soon. So once we get the request, we serve the prefix as like the initial part, and we already know that the other parts of this object would be requested soon. And this is like a preview or a motivation for our Act 4 of what we'd like to present, which considers predictive caching, or as Gil mentioned earlier, deciding to retrieve items or store things in the cache even though they were never requested before. So this idea of doing like proactive caching or prefetching has been used, of course, in many places, but specifically for caching, this is not something very common, or that we, at least as far as we know, that has been done or used, at least not in a general context. And again, the idea is to fetch items to the cache before they were ever requested. This occurs, for example, when you do like database scans or retrieve streaming data, or just retrieve large objects in chunks one by one, like one chunk at a time. So such sequences of requests for retrieving items do occur in many workloads. And I'd like to give you a little bit of reason to believe why this could actually work. So we've obtained a data set, an experimental data set for retrieving object chunks of objects, where every request can be described as like an object ID, like request I would be like an object ID. some offset in that object and some size from that offset that we're required to retrieve. And that's for request number I. And request I plus delta, after some delta requests after I, we get a request for the same object, starting exactly where this request ended, like offset plus size, and of the same size. This is like exactly a sequential access to object chunks of the same size. And we looked for such pairs. This is like what we considered a potential prediction pair. We looked for such pairs within this data set that we obtained, and we considered for every object, we looked at whether or not within the horizon of, like, say, the next 50 requests or the next 100 requests or 150 requests, depending on the horizon we look forward in, whether or not the paired request appeared in the data set. So for every request, we looked whether or not within this horizon we found the matching predicted pair. And we found out that actually the percentage of requests that actually had a prediction within this horizon looked something like this plot. Like, take, for example, this specific point. This means that if you look forward, like 100 requests forward, like within the horizon of 100 requests, 9% of the requests would have a matching request of this type. So this means essentially that if we were to allocate a cache, a small cache, to just like prefetch 100 requests according to this prediction rule, we might be able to obtain a hit rate of roughly 9% just by doing this prediction, just by doing this prefetching, this of requests according to this rule. Again, this is for this experimental data set. This does not necessarily would work for any data set, but this gave us a reason to believe that this might actually work and provide some benefit. So the idea is quite, well, similarly in a sense to what Gil described earlier, splitting the cache into like a regular cache, where when I say regular cache here, I'm not actually describing the specifics of what would be the eviction policy for that cache. Here we're doing this split across a distinct dimension. It's not like LFU, LRU, or other variations thereof. It's a large cache that would work as usual, and a small cache that we'd use only for items that we predict we'd like to insert into the cache and hopefully serve from the cache. So for every request Ri that we obtain, we prefetch Ri plus delta, and you can even assume that this predictive cache just works in LRU. So basically, like when you try to prefetch another item, just like drop, or even a FIFO rule could work here. In case of a hit, if we hit a prefetched item from the small cache, we promote it to the regular cache and prefetch the next request. So we like do like prefetching and prefetching and prefetching. We get like this sequence of prefetching that we do, and a prefetched item that is hit is stored in the regular cache, again, regardless of whether that cache uses LRU or LFU or whatever eviction policy or admission policy it uses. So, but what about large objects? So we had like large objects that we said, okay, but this takes up a lot of room. So for this, we're only going to cache prefixes. For what we're going to show now, we're going to combine these two optimization criterias and do prefetching, one thing, and the second thing would be when we cache things, we're only going to cache prefixes. So I remind you that this is the model that we're looking at, the streaming model, where we want to mask the latency incurred by accessing a remote storage, and we're going to focus on the wait time which is essentially the time for the first byte or the idle time in serving a client, where if we get a prefix hit, that would mask the access to the storage and would only incur a small cache wait time, whereas a miss would incur a large remote storage wait time. And you might ask, why wait time? Well, because when we do this for wait time, this does not depend on the object size. If we were to do this on the retrieval time, then if we have large objects, regardless of whether we say store the prefix or not, it would take a long time to retrieve just because it's a large object, and we wanted to isolate the effect of object sizes and just try to see how does storing prefixes help us in obtaining performance that is identical in a sense to storing the entire object in the cache, which is this perceived at the client if we were to store the prefix. So for this, we have only some preliminary results. Again, this is like things that are ongoing now with Red Hat teams that we're working with right now. So this plot shows us on the x-axis, we have like the size of the cache. And on the y-axis, we have the average wait time. And note that the values here do not start at 0. They start at like 180 and go up to 240. And for like the smallest cache size, having no prefix and no prefetch, which is these like triangles here, gives us a wait time of roughly 240 milliseconds, where employing both prefixes, actually employing prefixes with or without prefetching gives us roughly a 15% improvement in average wait time as perceived by the client in this streaming model. We note that the average wait time is essentially proportional to the miss rate, because a larger miss rate translates to a larger wait time. Having no prefix means that we're essentially using a smaller cache, because when we use prefix, we only keep parts of the object, so we are able to keep more prefixes of more objects in the cache rather than entire objects that might use up the entire or more parts of the cache and won't allow us to cache as many prefixes. You can see that actually just using prefixes gives most of the benefit. And prefetching helps a little bit more. If you employ both prefixes and prefetching, you get like the best across everything. But there is a small question is here of why is this gap so little? I mean, why do prefixes give us most of the benefit and prefetching only gives us a little bit more on top of that? And the reason is that if you recall our algorithm or our reason to believe is that if we get a hit, we promote to the regular cache. Now, doing these prefetches, some of these prefetches are actually already in the regular cache to begin with. And when we took a closer look at the trace and analyzed it, we noticed that and the resulting performance of using our caching policy, which here actually was just LRU. Again, this was like a very preliminary evaluation of what we can do here. The actual potential that we get is actually only 3%. Although this seemed like there's a lot of potential from predicting and predicting correctly, the actual potential of items that were hit in the prefetch cache but not available in the regular cache was only 3%. So that's the reason for the fact that we do get some benefit, but it's not very large. This is like another, what is it, like 5% or something that we get extra from this. Good. There are a lot of challenges in predictive caching, which some of them are clear. And one of them, and like for us, in a sense, maybe the biggest one is use cases, just having use cases. Like if we want to show that this could actually work and it's beneficial in several, hopefully even many scenarios, we would need a pudding to show the proof. And this is like an open call for all of you here in this talk. If you have interesting use cases for that you'd like to examine or test, and you'd like to share some like data or even distributions, we would be very, very, very happy to cooperate on that. Another big challenge, of course, is that good predictions might require statistics, and obtaining these statistics beforehand might not be very, very simple. I mean, we examined this trace that we had in order to see that there is a reason to believe that this would work there, and it does work. But actually knowing this beforehand is not trivial at all. It's not clear if, I mean, what are the questions that we should be asking for every trace. Here are pairs of prediction pairs were very, very simple, rudimentary, like it was a very simple approach. Other traces, of course, might require much more complex dependencies and prediction patterns. And for dynamic policies, which is like the holy grail, as Gil described earlier, we would like to learn these patterns as we go along. And here again, it's not very clear what are the best approaches to doing these things. Are they just like simple statistical approaches that might work? Do we actually need like heavy machinery, like ML-based heavy machinery for doing this? These are all questions that we do not know the answers to, but we are working on these questions right now. Questions?
Yeah, so this is a perfect time to ask questions, and in fact I have one. So you mentioned during this talk a lot of different algorithms and approaches and methods, and there was some discussion in the chat regarding the place where all this stuff is implemented and available in open source, and where we can download it and play with it and try it out. And Gil even put a link in the chat. So just to make sure, so where we can get all this stuff, and what is this caffeine library, and whether all the algorithms that we discussed are in there, or there are some other sources. How we can get access to this?
So caffeine, I mean, Gil might want to answer. He knows caffeine better than I do, but basically caffeine is available in Git as an open source project, and the implementation and many of the algorithms that were described here are actually already implemented there. And there's also a simulator there that you can actually try to see if that would work for, or what would work best for your workloads for all those policies that are implemented there. And this is, again, ongoing work. I mean, we're trying to push as many things into that library as we develop more solutions and more policies in order to have them available as open source for the community. So, I mean, that answers the question.
Great, thanks. So let's
and
proceed.
Thanks, Peter, for the pointer on the NSDI paper. Thank you.
So let's proceed while we're giving the people an opportunity to type their last questions in the chat or to go live and ask.
Yeah, so I'll just maybe wrap up with a few takeaways from today's talk. So the first one is that heterogeneity is everywhere, or as Brian used to say, you are all individuals, you being places where things are stored and items that are stored and their characteristics in the way they affect the system performance. So heterogeneity is really, it's really there. I mean, it's something that we have to handle face front and develop algorithms that take these heterogeneities into account. The second one, which again might be trivial to some and not very clear to others, is that caching is not just LRU, although it is very, very popular, very simple to implement. It's really everywhere. There's a lot of there are a lot of things beyond LRU, and some are not that intense in terms of it's a good suggestion to try them out and see if they work better for your workloads, for your applications, for your needs. The third thing is dynamic policies that self-adjust, that tune themselves automatically. They react to the workload. They work for whatever workload, even if that changes a long time. Most of the policies that we described here are such policies. And in a sense, you get the best of both worlds, of all worlds. It's true. It's important to remember these are not optimal, as Gil stressed in his talk, in his description of things, but they try not to lose too much. And even if they don't converge, they are, I mean, their state is in a good working environment. Okay, I mean, it's a good range of values for which you'd get most of the benefit, if not the optimum benefit possible. Deciding where to look is important. In a sense, anyone can be an eitzes giver, if you pardon my Yiddish. That means that you try to retrieve something. There could be a lot of options, certainly in distributed systems, where you can retrieve it from, and making the right decisions might have a significant effect on the performance of your system. And last but not least is that predicting the future is the future. And we are, again, currently working on these questions of how can we predict which item to cache, even if it wasn't requested in the past at all. And we don't even know that it exists in a sense. And with that, I thank you. And if there are questions, then we'd be happy to answer. These are a few pointers for the Caffeine Java caching library and for the joint project that we're currently running with Red Hat. I think the presentation will be available later on online, so you can just click those links and have them. And with that, that's it. I mean, again, if there are questions, either Gil or I would be happy to answer.
We do have questions, in fact, but Gil is taking great care of them in the chat. So thanks, Gil.
Sure, why not? I like questions.
So with that, I think we are starting to run a bit out of time, although we can still accept a few short questions. I would like to thank you, Gabi and Gil, for being here today, and also to the audience for staying with us until the end. So thanks, everybody, and we'll be happy to welcome you in our future events.
Thank you. Well, on behalf of both Gil and I, thank you for inviting us to give this talk. I mean, it was fun thinking about what would be interesting for the very heterogeneous audience that we might have here. And again, we would be very happy to share and to go on and cooperate with any of you working on similar topics or having similar problems. So thank you all again for joining.